Welcome to the GOTO Podcast. Each episode covers the brightest and boldest ideas from the world's leading experts in software development. Tune in for practical lessons, compelling theories, and plenty of inspiration. GOTO gathers the brightest minds in the software community to help developers tackle projects today, plan for tomorrow, and create a better future. Stay up to date with the latest in tech through GOTO's top-rated events held online and in person in cities like Amsterdam, London, Copenhagen, and Chicago, and by subscribing to the GOTO Conference's YouTube channel, where you can find thousands more high-quality dev talks. Learn more at gotopia.tech.
I am Richard Feldman. Welcome to this book club interview. So I am the author of Element Action, which is not what we're discussing here. We did a separate book club on that, but from the same publisher, Manning Publications. Tim is the author of Rust in Action. You'll meet him in a second. And this is a totally different book and a much different audience. So we're going to talk all about the book and what motivated him to write it and all sorts of things about the process. And I'm really excited to talk about it because I also am a big fan of Rust. I teach a course for front-end masters called Intro to Rust. I've written a compiler in Rust. Big fan of the language and really excited to talk about it today. So Tim, do you want to introduce yourself?
Yeah. Hey, thanks, Richard. So my name is Tim McNamara. I am a developer based in New Zealand, but prior to Rust, I was a Python developer, primarily in like the data science space. And a few years ago, I was sort of like scratching around for trying to figure out like how computers actually work. And then I kind of accidentally got asked to write a book. So that's kind of the pitch for Rust in Action. If you are from sort of a dynamic programming background, or even say a Java, but you've never really encountered these terms systems programming or any of the concepts around that. That's really what Rust in Action is trying to provide a little bit of a glimpse in, to not so much teaching you systems programming. It's primarily there to teach you Rust, but it uses concepts like drawn from sort of that subfield to really kind of enable you to feel welcome inside the Rust community.
Nice. Yeah, well, so let's talk about that a little bit more. So you said your background is kind of a Python developer. I actually came to Rust from a similar perspective of not really having done any kind of systems programming. Like I knew C and C++ from a long time ago and kind of had a bad experience with them, to be honest. Didn't really have any interest in getting back into that world. But there was this kind of curiosity about, I've always, for my whole career up to that point, I'd always been on top of some sort of virtual machine or interpreter or something like that. And I never really knew what was going on under the hood. And that was always something intriguing to me. It sounds like it was for you too. So how did you actually go about like learning Rust yourself? This book didn't exist, right? There was no, we got it right here, Rust in Action, right?
Nice.
I've
got my copies down the back. I should point out.
But it didn't exist obviously because you hadn't written it yet. But there's all these resources out there. I mean, there's like the official like free Rust book that you can read. Other people have written Rust books. So I'm kind of curious about, what was it about that sort of motivated you to write the book in this way? Like, what did you want to sort of accomplish to present people with something different than what was already out there?
Right. So the very end of your question kind of hinted at the answer, actually. So I'm like one of the last people to learn Rust without the book, the official The Programming Language, the free one online. I actually intentionally didn't refer to that at all because I was overly concerned about like copyright protection and things like that. I didn't want to plagiarize other material.
Oh, interesting.
And same with the O'Reilly book, Programming Rust. So it turns out there's like accidental plagiarism. It turns out that the Rust in Action, as well as Programming Rust, the O'Reilly book, have like a renderer for the Mandelbrot set. My one happens to be inside the terminal, and I was like after the publication, after my book was published, I was like reading through the others, and I was like, oh wait a minute, that was maybe a mistake. But to answer your question, I really wanted to produce a book that was different than every other book I'd ever seen. So I kind of, and from like a marketing or like perspective, I didn't want to write like a Me Too book. I couldn't really compete with the official reference, so we could, or like the official guide. So I can't write a book that just takes you, let's say, start with integers and then we get to floats and then we get to strings and then we like have structs and we combine them together and then we might talk about traits. Like I can't write that book again. Like that doesn't, it's impossible to really compete with free, essentially.
Sure. Unless you're doing something different.
Right, exactly.
Yeah.
And so Programming Rust from O'Reilly was the other one that was coming out, and Manning was really concerned. Like, we're really got to get on this Rust space. And that was really focused on C++ developers who were kind of like Rust curious, let's say. Like, shared pointer. Like, or so if you're not familiar with Rust, Rust is it's really protective of data access. C++ in a very broad way is less protective of you, the programmer, for when you want to access variables, particularly across threads, and you end up they clobber each other. It turns out you don't even need multi-threading to cause these kinds of problems, because we have multiple CPUs that might also want to access the same variables at the same or roughly the same time. Anyway, ignoring all that, Rust has these kind of really strongly enforced guardrails that you need to intentionally opt out of, whereas in C++, you need to opt into the guardrails, essentially. And there are some types and that exist in C++ that are ubiquitous in Rust. Now, the reason why you're a C++ programmer and you might look to, say, a Rust is that C++ is notoriously difficult to get right. And maybe this is what you're referring to when you were saying, like,
I mean, I think I have a concrete example of that is that I remember when I was doing, many years ago, like a little bit of C and C++, is I would all the time get a program crash that would just say segmentation fault, meaning that I did some stuff with some memory somewhere that I wasn't allowed to, or I made a mistake somewhere. And then figuring out what the actual underlying problem was behind the segmentation fault was often very time consuming and painful. But when I moved to, higher level languages that had automatic memory management, if I ever saw a segmentation fault, it was never like, oh, I made a mistake. It's like somebody who implemented something that I'm building on made a mistake. Somebody else made a mistake. I don't know who, but, and it was super rare. And that's also been my experience with Rust is that, I mean, there is the whole like unsafe section where you can definitely cause segmentation faults. But if you're staying away from that, and at first I just avoided unsafe keyword altogether. I found that, I can just feel that I will be able to write my code and maybe the compiler will complain at me and say, you can't do what you just tried to do. But as long as I can get everything to compile, it's not going to seg fault. It's not going to like catastrophically blow up. And if it does, it's because somebody else made a mistake rather than me making a mistake.
And the same with me. I was writing Python and I had these jobs that were running for like 3 or 4 hours and then they would like crash with a name error or like like a type error. I'm like, how did this happen? Like, and it just blows up in the exception and then is there. And like what I wanted from a language was like something like Elm. There was like developer happiness is actually paramount.
Yeah.
Like, and actually error messages are part of the language and the error, like debugging experience is actually part of the design of the language.
Right.
And what I kind of got from like a Rust was much closer to an Elm experience versus like a C or a C++ experience where things would just blow up even without it. Because in C, where I tried to play around, I tried to write Python extensions in this C macro language called Cython, which essentially is C with Python syntax.
I've heard of that, yeah. Right.
But again, it blows up spectacularly and you like literally don't know what to do. It's like, okay, segmentation fault. What do I do now? Like, is that the end? Like,
right.
And so,
and I mean, what you're supposed to know is it's like, well, now you need to attach a debugger and go back through and step back into it. And then like, but it's this whole complicated thing. And then even once you know how to do it, it's still pretty difficult to track down like what was the actual thing that caused the memory to get in this bad state.
Right.
It's really a whole different level of pain.
Absolutely. So one of the things that I was really curious about is like, what does this term segmentation fault even mean? And that's actually one of the things that I explain in Rust in Action. We actually, and like I think it's chapter 5 in data, we actually talk about the fact that memory, like, needs to be translated in your program. We talk about a memory address as an integer. So some integer between 0 and 2 to the 64 minus 1. Like this is what we call our address space. But somehow that needs to be translated into something that's like physical electrons on a chip somewhere. Now, that translation process is complex and actually involves software, which is kind of like a bit of a weird mind bend. But it turns out that the operating system segments memory or like into 4 kilobyte chunks. And the segmentation fault is a problem caused by when you're attempting to access a memory address that sort of doesn't actually, the operating system doesn't really know how to translate into like physical chip. Like it's something actually on RAM. It can be more complex than that, but
or you're not allowed to. Yeah.
Right. Yeah. The operating system will also enforce that there are some parts of the memory address space are actually inaccessible for you. So it turns out that the operating system can mark some sections of memory as executable, some as data, and some as code. And like all of this background knowledge that you're supposed to somehow acquire is kind of what I wanted to inject into the book. And part of the problem that I faced as a writer or as an author was that I was always late because I was essentially trying to write like 2 books in one. And by the way, I also, the other thing that I tried to do really differently than most other books is like pack in big, like relatively chunky examples. But it turns out that that's hard because you kind of need to debug them, and you can only really introduce.
I remember this.
one new language feature at a time. Because if you try to pack in two new parts of the language into a new example, well, suddenly you've got like 5 extra pages of writing you need to do in order to explain people. And people, like, they have this kind of mental stack, and you're only trying to add one thing at a time and kind of give some. Anyway, that's why I thought that providing this sort of extra context around Rust would be helpful.
I think that's really cool. Like you have this cool example in here. There's awesome examples throughout the book, but like here you have the title of this section is All of Networking in 7 paragraphs. And you got like just a diagram. It's like, look, here's how your network stack actually works. It's not, it's not just a Rust book. It's a combination of, while you're learning Rust, you're also learning about low level parts of the computer, which I love because that, I think for a lot of people who are in the position that you and I were in, coming from like high level languages and being like, I want to learn about this low level stuff, but I don't want to deal with segmentation faults as errors like to my program, or maybe I just like want to understand them better, and while also not having to debug them. That's great, and like that certainly was not a resource that existed when I was getting into Rust.
I want to also just kind of segue slightly into talking about the cultural differences between programming language communities.
Sure.
Because I, as a Python developer, was always told native extensions are difficult. This is for experts. I had some encounters with actually a couple of other language communities where I would say things and I would kind of immediately get pounced upon because in retrospect, like the whole, like, because I didn't have the mental model, I didn't use the language in the right way. And so therefore people didn't address the question. They addressed the inaccuracies because I used the words wrong. Whereas I feel like, and I'm very clouded now. Like I'm very deeply embedded in the Rust space. And I'm very hopeful that new entrants to the community still feel this way. My experience was that the Rust community was particularly welcoming and particularly interested in preventing people from feeling excluded. And that's kind of baked in with the slogan.
Yeah.
Like empowering everyone is how it starts. And you, as someone watching this podcast, you as someone who is curious but a little bit fearful potentially, or maybe fearful's too strong, just a little bit hesitant, should feel as though you're welcome. And part of the book is to say, or at least part of my rationale for creating something new and interesting and different was essentially to say that, is to give people confidence to learn more. Like, I can't teach you all of Rust. In fact, there are some parts of the language that I exclude from the book.
That's a beginner book. I mean, you can't you can't simultaneously give a good introduction and also cover absolutely everything there is, right?
Right. There are typically two complaints. Like, about 95% of people are really, really happy, but there is there are complaints. And the two themes primarily are, A, why isn't your book like every other book? Like, this is not something that I'm familiar with. I'm used to being able to like pick things apart. It's like, well, I wanted to look up like what an enum is in Rust, or like, so where is that? Like, I can't find that in the contents page. And I sort of feel like that's slightly misguided. I want to say that, well, you kind of didn't read the first introductory thing, or it was like, who is this book for? And the other complaint, I guess, would be that it's too introductory. Like, it's like, this isn't a guide to writing idiomatic, high performance, zero copy Rust. And I also feel like that's slightly misguided. And so I'm pretty happy with the reception to the text in general.
Well, I think, I mean, if one of the biggest complaints is I wanted you to do even more, that kind of tells you that, like, well, you did a good job with what was there. They wanted more of it, right? It almost sounds like what they're asking for is like, hey, can you do another book, advanced to us? How about it, Tim? Just kidding.
Well, like, I should actually say, the decision between, do you do a second edition? So there are things that have changed very slightly, but primarily in the libraries, the ecosystem has matured, and therefore things, essentially, I can sand off some edges and create a second edition. Or do you essentially do like a second volume, or like another book, like a follow-on? Right. I told Manning, I've got 3 little girls. I don't think I can get you a book on time. Like, let's say in the space of a year, 18 months. Right. That's a new book. But I can do a different edition. And so very, very, like, within a couple of weeks, you should see an announcement of Rust in Action second edition, like, appear on Manning's website. But I'm also interested in potentially fleshing out some of these next ideas via, say, my YouTube channel potentially, or like relatively thorough blog posts that I'm hoping to somehow combine at some stage, or kind of distill into a book over time.
Yeah, that makes a lot of sense. I think I got a little bit lucky with the workshop that I did on Intro to Rust, because it's very time limited. It's like you have like an 8-hour workshop, and like that's it. There's no, hey, I wish you could have, had it be longer, because it's like, well, now it's a multi-day workshop. This is one day. And I mean, I had like way less scope in that than you have here in Rust in Action. First of all, I didn't have the like practical examples so much. It was more just like, okay, we got to get through. And I mean, I'm kind of curious to talk to you a little bit about your sort of thoughts on, how to teach Rust effectively to beginners, because what I found challenging, so this is front-end masters, it's a primarily JavaScript audience, and a lot of people are interested in Rust because like a lot of JavaScript tooling is moving to Rust, and there's, applications of WebAssembly and things like that. But what I found after doing some practice runs of that was that it was just hard enough to get, I basically pared it down all the way to like, okay, I have 8 hours to get to lifetime annotations. If you can understand lifetime annotations at the end of 8 hours, starting from no Rust knowledge, then I succeeded. And I was like, traits out the window, no time for them. Everything else is just all the way building up to that. And now if you want to understand lifetime annotations, you can at least read the documentation, and now you can kind of go off on your own. But you've managed to pack a lot more scope into here. But I'm curious what you thought were, for me, that was the hardest thing to build up to, because it requires all this background understanding. What did you think were the hardest things to teach in Rust?
Strings. Actually,
yeah,
right. So I've got I want to provide a little. So I fought really hard with this idea. So I was convinced that I don't want to teach strings after numbers. So normally you see a programming language tutorial and they introduce numbers first because they're easy addition, so forth. We have a little toy calculator, and then the next thing we do is text. It turns out within Rust, knowing that you need a distinction between like a string literal is a different type than a string, which is kind of super weird. And by the way,
like if you had a Rust REPL and you put a string literal into it, you type it "hello world" in quotes, it's not going to come back and say, "Oh, this is a string." Nope.
That's right. Yeah. And then there are really sound. This is going to sound ridiculous. Yeah. There are sound technical reasons why this is the case. Essentially,
absolutely.
It bubbles up a lot of the implementation details about how programming languages and how programs are built. So into the programming language, because Rust always wants to offer you the choice to kind of boil away the abstraction and go right to the depth of what's actually happening. So just to kind of flesh that out. So a string conceptually is like a list of characters. But it turns out our conception as someone, we're probably from like a Western Latin script, or at least we're used to having this conception of written language as like one character after another. It turns out that there are many scripts in which this doesn't work. And therefore we need a character encoding, which is a way of translating numbers to sort of symbols, which we'll call glyphs. And that particular system also needs to be backwards compatible with the way that people have been using computers for decades. And so we have this way of encoding what's known as Unicode, where we can kind of encapsulate all programming languages ideally inside the computer. And we also need to so we get this thing called UTF-8, which can kind of expand out. But again, it's one character after another. But where does that live? So if you are a programming language, you need to decide where to put this in memory. And it turns out that a function is a special kind of section of data. Your programming, I'm trying to get the semantics right. The compiler, let's say, is trying to decide, I need to put, for technical reasons that relate to the CPU, your CPU, when it calls a function, what's happening is that it's jumping to a memory address, and then return is kind of popping back off and going to the last place. In order for that to happen, the function needs to be of exactly the right size, and it can't expand or contract. That conflicts with our notion of like text. Now, text, we can append to the string, we can concatenate with other strings, we're used to kind of manipulating them. So that we actually need to put the string in a different part of memory. And what we keep inside the function is a reference to the malleable string. So we've got a reference in there.
But then you get into the performance issues, right?
Right.
You can put it on the heap, but
it turns out that there's a third spot. So we think as programmers, there's the heap and the stack, which is explained again in Rust in Action, or like you can look up any introductory systems book on what these terms mean. It turns out there's like there are a couple of extra. There are a couple of that's right. Shared libraries, for example, live in their own part of the address space, but
global variables,
with global and we have a region of memory called static for kind of weird esoteric reasons. It's
that's what Rust calls it. Yeah,
it's like the read-only section of memory, right?
Right.
And
it's part of the like actual compiled executable. Like when it's on disk, right?
Yeah.
Like that string, if you say hello world and you put that into your program, the string hello world, the bytes for that are actually in your compiled Rust program on your disk. And then when your operating system loads the contents of that file into memory, it's like, it's right there in memory now. It's took it from disk, moved it into RAM, and that's where it is now.
Yeah.
Not the stack, not the heap. It's just, it was on the disk and now it's in memory. That's it.
So to pull this back to string literal, your string literal lives in a different place entirely than most other strings, at least what we think of as like the string type. It turns out that they can kind of be unified through a reference to some array. Let's use that term, like some list of characters, of bytes that happen to be encoded as UTF-8, which is this encoding for translating numbers to what we would say is like a writing script. Now, all of these so we've got like 4 or 5 different forms of translation happening. And this really sucks up people's working memory when they're learning something new.
Well, I think especially because like hello world is such a canonical, way to start off a program, and because if you're trying to explain the types of things, it's not just that the type is not string. The type is ampersand, apostrophe, static, space, str, all lowercase. And then the whole library uses things called string, string, capital S, no static, no ampersand, no apostrophe. It's like,
what's going on there? And this is your point of like, well, maybe lifetime annotations is enough. Then the question is like, what on earth is a lifetime annotation? It turns out, like I know kind of maybe conceptually like that variables have a type, but a lifetime? Like that's kind of weird. And the syntax is ugly and weird. And by the way, this term static is kind of this weird magical term for, by the way, lives forever, or at least from this point on until the rest of the Rust compiler has like a sidecar part of it, or essentially like a really strong linter called the borrow checker.
That's a good way to think of it. Yeah.
And the borrow checker's job is to analyze your program and say for all invocations, or every single time for all possible invocations of this program, is every data access valid? Right. And can it ever possibly be invalidated? And it turns out that if in my function, well, let's say I create a variable ref, and I'm creating a reference to some other data. Now, the borrow checker, and for kind of weird esoteric reasons as well, which happen to be slightly historical, we call this a borrow. I have a reference to some other data that lives outside of my function. The compiler guarantees that the data that I'm referring to will sort of never disappear.
Right.
I will never get a segmentation fault in Rust because I can't accidentally what's known as free the memory. So I can't actually return it to the operating system and tell the operating system I don't need this anymore. And so invalidate my reference. This is impossible to do in Rust. All of this kind of boils down to a lot of complexity is sort of front loaded as a learner. Yeah. My job, by the way, so Rust is, so this book, Rust in Action, has been really good for my career. I've scored a couple of really neat jobs out of it, and nice. not exclusively, but I am a relatively competent developer as well. I work at AWS, and AWS is kind of doubling down, or Amazon broadly is doubling down on Rust. And my job this year is to create like an education program for Rust, primarily focused on people who are learning or have been used to Java, JavaScript, TypeScript, Python, are the kind of the other primary languages. And so this question about like what people need to know and like where they get tripped up is like really front of mind at the moment for me.
Yeah.
So I think that you're right about lifetimes. The thing that I'm really struggling with is sort of sequencing. So there are...
It's always hard.
Because there are so many parts to Rust, And there's also some really, really good parts. So one of the things that you forget when you hear, oh, Rust is really hard to learn, is that actually it has a lot of niceties as well. Like
True.
enums and pattern matching, for example, are something that
Yeah.
I just think are incredible. And I really miss when I go back to other languages. So, for example, conceptually, if I've ever used a language with an exception construct, Rust doesn't have exceptions. And so you can get this cultural mismatch. Like, well, what do I do if I might get an error? It turns out you can just return those as values.
Right. Well, but importantly, they're not, because I think if I were coming from like a Go background or a C background where errors are returned as values, I might think, this is not going to be good, because what if I forget to handle it, right? But the way that Rust does it, it's not like that at all. I mean, you cannot forget to handle it. The compiler will be like, you forgot to handle this error here. You need to do something about that.
And what's really amazing to me, so you will for every function that might create an error. And so this primarily you'll encounter this when you're learning, when you deal with the file system. So essentially you consider like anything saved to disk as flaky, like it could potentially fail. For many reasons, you might not have permissions to open files. There's a whole bunch of reasons why things could fail. And so there might be not enough disk space. Who knows? I mean, disks are pretty big these days, but
lots of reasons though. Yeah. Or you could be on a virtual machine, and the virtual machine's disk is very small and limited.
Interesting. Oh yeah, no, that's right. It's just virtualized away. There might not even be a disk, right? Rust will guarantee, it'll say, look, by the way, that IO function, like the function dealing with input-output, returns something that might fail. Dear programmer, you've only addressed the case where everything is on the happy path. I'm going to refuse to compile now. What I love about this is that this is actually known in Rust as the result type. So result is normally going to be okay, and everything's going to be fine, or it might be error. And on the error side, you might think, well, it's so fundamental to the Rust way of thinking now that you kind of think of it as being part of Rust. But it turns out that result is defined in the standard library. It's actually not part of the Rust language. It just falls out of enums. So part of I think the magic of the Rust, the language, is that there are these really powerful constructs that are consistent and embedded in the way, like the practice of writing Rust, and primarily Rust result, but also option, which is a similar but different type that encodes the possibility that there's a missing value. And I think it's just wonderful that instead of just like the Python like none, or like JavaScript like null or undefined, like it could be essentially throughout your entire program.
Right. And I think it's interesting that some modern languages are starting to adopt some of these things. Like Java now has an optional type, which works essentially, as I understand it, the same as Rust's option type. The difference is that Rust uses this exclusively. It's not like Rust has option and they also have null and they also have undefined and they also have another way. It's like, no, there's just the one, there's option. Whereas in Java, you do have optional and you also have null, which, for legacy reasons, if you want to argue it that way, it's like, well, you still have to be aware that nulls might happen. Or it's like, no, you don't. You don't have to be aware that nulls might happen. That's not a thing in normal Rust code. Now, granted, if you do specifically have a Rust pointer, that can be null. Okay, fair enough. But now we're already in unsafe territory.
Yeah, essentially what you're saying there is, well, you've kind of, if there are ways to kind of unlock the Pandora's box. But if you're doing that, it's intentional, right?
It's interesting, like you were talking about earlier, like in Python, it's sort of culturally a thing that if you're going to do, interop with another language and drop down to the lower level stuff, it's like that's kind of for experts and to hear there be dragons. But to me, it actually, at least when I was getting into Rust, I felt the same way about unsafe code, where it's like, well, I'm doing low-level stuff in Rust, but there's still this other level that's deeper and scarier where I use the unsafe keyword, and now all bets are off. We're back in segmentation fault land. So it almost feels to me like somewhere in between, like a Python or a Java or something like that, and the lowest level, like assembly language, machine code, C, which is just portable assembly, as they colloquially say. Rust is somewhere in between. Like it is definitely lower level, a safe Rust, I should say, like when you're not using the unsafe keyword, it feels a lot more like a Python or a Java within a lot of ways better ergonomics, and a higher learning curve. But at the same time, I get almost all the power of that lowest level stuff. There's just this little extra bit that requires going into unsafe if you really want to get into those things.
Yeah. So this is actually one of the things that I intentionally included in the book. That I was really actually I got quite a lot of pushback from reviewers. So Manning has this process where they send out your manuscript to say 20 people that anonymously provide feedback. And one of the reviewers, it's like the opposite of fun, right? No, it's a really important part of why Manning's books are very high quality. And one of the things that I stayed quite firm on was exposing readers to unsafe. I was like, this is a valid part of the language, and we shouldn't be kind of intimidated by it. Or at least, and like there are some really powerful things that this unlocks. And one of them, or at least if we ever, like, for example, one of the examples is like a memory scanner. So actually we want to invoke segmentation faults and kind of like find out like where things are and like we kind of need to do silly things like converting integers, like raw integers into memory addresses, for example, and which means we need to kind of lie to the type system or like lie to the compiler.
Right.
From like a teaching point of view, I did also want to say that you shouldn't feel as though this isn't something that is learnable. I just had a slight flash of a thought, which was one of the reasons why you might want to do unsafe. Well, actually, you probably don't want to do it, but one of the things Rust does badly by design, essentially, is cyclic data structures or like a graph. So when you have, normally things in Rustland like to be in a tree. As soon as you have references from children back to parents, you create a cycle. And those sorts of cycles turn out to be quite nasty in languages that don't have a garbage collector like Rust.
That's definitely an interesting... I'm surprised, first of all, that reviewers would push back on that. I mean, to me, it seems like there's an open question of like, should a beginner book get into this or not? But it seems worth mentioning at the very least, especially because I think there's a lot of misconceptions out there around unsafe. Like Steve Klabnik wrote that whole blog post about you can't, quote, turn off the borrow checker in Rust, which is not what unsafe does. It's like the borrow checker is still very much there. There's just certain operations that are unsafe for potentially other reasons or potentially a lot of reasons that require the use of the keyword. And I think it's helpful, if you have time to do it, to explain to readers, here's what unsafe is, even if you're not going to, go on a whole long tangent about here's all the different things you can do with unsafe. And here's, or especially, giving people the wrong cultural impression. Because certainly from what I've seen in Rust is a very strong cultural aversion to using unsafe. And really people want to see that, a library that they're depending on is using it as little as possible.
Right. I don't want to give people the impression that unsafe is essentially unsafe is going to ruin your program. And I think what you're trying to say there, Richard, is that it's very easy for tooling to detect the use of unsafe. If libraries are known as using this construct, it means that it becomes like a very strong target for like refactoring. And this happened with like a very prominent web framework called Atrix, which had extremely good benchmarks. But kind of the immune system of the Rust community kind of came back in some ways and said, whoa, you're faking it. Well, not quite. It turns out that there were good reasons and so forth. And it seemed like this big cultural war around what is
it's a big controversy.
That it was quite big. I mean, it was there are like programming language drama.
Of course.
And so, but I kind of do feel like explaining a little bit about what's safe. So there's two uses of the word unsafe. So the keyword itself says not this is inherently unsafe. It's more I as the programmer take responsibility for verifying everything that the compiler would by itself verify. So remembered why we had like this very strong linter called the borrow checker. Now, essentially, you as the programmer take on responsibility for being the borrow checker. That's essentially what unsafe is used for in the primary use of that keyword. It doesn't provide you like a free-for-all to do everything. Like, that's what Sue's post was about. And it's intentionally ugly. So it's actually really hard to just kind of accidentally insert. The other use of unsafe is you can define a trait. So this is kind of an interface or an abstract base class that is unsafe. And what this is actually subtly different use of the keyword. What this is saying is that people that implement it need to guarantee that their implementation sort of complies with a contract that is probably written in the documentation, because the type system can't really encode it. That's kind of my understanding of the two big reasons of why you might want to use the keyword.
Yeah. So one thing I want to make sure to ask you about is in the timekeeping chapter, you have a photo about a physical device that keeps time. What's the story behind that?
Okay. So you just get me to geek out on like another one of my like big passion projects, I suppose. So this is from so I'm quite into I guess nature protection broadly. It is from it's a box, and inside it's a device that takes infrared cameras from a project called Cacophony. It turns out that when European settlers arrived in the 18th century into New Zealand, they introduced many over the course of about a century, they introduced a lot of species that were really harmful to a lot of our native birds. Things like stoats and weasels and rats really like to eat either birds or eggs. And turns out that if you're a flightless bird, this is bad for you.
Yeah, I bet.
So there was there were some diaries of explorers, and one of the phrases was that, at night, the forest was just this cacophony of sound, and the whole forest was just alive with birds. We didn't have any predators at all, so a lot of our birds are actually nocturnal also. So famously, the kiwi, the bird with the long beak that can't fly, is actually a nocturnal species.
Didn't know that.
There are a lot of adaptations that are quite strange, by the way. So we have birds that pretend to be rodents. We have birds that can hop around trees, so they're kind of similar to monkeys, or provide the same. They live in the same ecological niche, or provide the same function as what mammals would in other biospheres. Anyway, the Cacophony project is attempting to use machine learning to identify, is this a cat? Is this a rat? Is this a weasel? And it does it with infrared vision. And it turns out, so it takes photos or takes videos actually, and timestamps them. But it turns out that if you're a tiny little device, it's really hard for you to tell time. You need a clock. And then I was like, wait a minute. So part of this book was just amazing research. And I was like, how on earth does any computer tell time? And it turns out one of the properties of quartz crystals is that when they are electrified, they oscillate. So they go backwards and forwards at a very specific frequency. And that frequency is counted. And therefore, we know the voltage that is being sent into the crystal. We know its rate in which it will oscillate. And therefore, we can tell time because we say we started at 0 and we just start clicking across. Eventually, we will hit some number. Let's say we have like 16 bits. We'll get to like we'll get to 65,000 and we'll need to wrap around to 0. But we might have some way of dealing with that. It turns out they do. But it turns out this essentially really, really primitive, a way of keeping time is actually used by essentially every digital computer. But then how do they synchronize? And this is one of the problems about distributed computing. So how does everyone say, okay, I'm currently at, let's say, I'm currently at oscillation 25,000 of my current cycle. Okay, how does that translate to the 6th of March, 2023? it's all distributed. I'm going to get into a big flame war, but essentially, we have is canonical devices. So much more accurate timekeeping devices that are what are known as atomic clocks that use even more specific, and they all kind of agree. And it turns out that I think there's about half a dozen, maybe a dozen of these atomic clocks that they're called tier 1 devices or tier 0 devices inside the network time protocol. And they agree on what the time is.
Right.
And then they just tell other people. And then just like, let's say, a DNS system, it kind of propagates through. It turns out that if you are inside a data center, you can get clocks to agree on what the time is without because it somehow at some point it kind of becomes irrelevant what the atomic clock thinks the time is. What really matters is that the clocks that are really close together agree, because you want, say, for example, logs or messages to be roughly in order. It turns out you can't really do this.
Right, monotonic ordering.
Yeah, like in a distributed system. And it turns out, by the way, like a single multi-core laptop or a single multi-core phone becomes a distributed system because each CPU operates independently. And this is kind of like one of the mind-bending things about technology. Like, it's just so incredible that like this stuff even works.
Yeah.
And like, I just think about it, like at every single level, you have these examples where you at every single level, like think about text. We started with like plain bytes, and then we started with like Morse code and other coding signals for interpreting like binary digits and translating them to letters and numbers. And then we kind of like wrapped around more and more on top. So in ASCII, which is like the encoding system from the 60s, there are control characters, and we still managed to kind of hold on to those, even though like the bell doesn't mean much today. And famously, operating systems still can't agree on what a new line means. But do we need a carriage return and like where there's no physical carriage?
Depends on which operating system you ask.
That's right. And like, somehow we've just added on more and more layers, and like again and again. I love it. And like and that is kind of why I was like, you know what? I am going to spend essentially years of my life writing a book. So I did some calculations as I was like in the final stages of processing, like, or publishing, about how long this horrible project took. I spent on the average week between 10 to 15 hours per week on this thing. So 3 or 4 hours a night, 3 or 4 nights a week. Plus I'd try to do like a chunk in the weekend. From the initial conversations with Manning through to publication, it was essentially a 4-year project because I needed to like do extensive rewrites and like of both the prose as well as the code, and answering lovely questions from like people reading it as well. But it was always that was a bit of a time suck, and like doing diagrams took weeks and weeks and weeks in some of them.
I remember all the diagrams. Yeah, those are. It's like they don't take up that much space on the page relative to how much time they take up to make.
Yeah, that's right.
In a lot of cases.
So I was like, I've probably dropped like 2,000 hours into this thing.
Well, that's a great segue into my final question for you, which is, looking back on how much time you spent into it, was it worth it? Are you happy with the result? You mentioned it was good for your career, but just as an author, like, what? Yeah. So what do you think of the whole process?
You've picked up from this interview that I learned a tremendous amount through the research process, through like the writing process. I became significantly more skilled at communicating. I always had the goal that I would speed up people's learning journey by 100 hours. At this point, I know that potentially hundreds of thousands of people have read the book, and that is if you were to multiply my input versus the output that it's generated, I think it's been like a huge win for the industry. It's created a whole wave of Rust material inside Manning and other publishers who have said that Rust is a viable product or like is a viable ecosystem. And I think so. The only thing is that my health suffered quite badly. Like I used to run marathons. I used to lift weights. I used to be able to pull like 200 kilograms off the ground. I basically put all of that aside. And I think that my kids are the people that suffered the most. And because there were times when we could have gone to the park or we could have gone for a walk. And I was like writing the book. And so my message to readers is like, I hope that you find the material that's useful for you. It might be Rust in action. It might be something else, but find it. Like this is a community that is welcoming and accepting of you. And there is like a large, there are now like a very rich set of resources to draw from. And I think my message to my kids is that like, I love you lots and I hope that you forgive me.
Yeah. Well, I'm glad that if you're going to make a big sacrifice like that in so many different aspects of your life and your kids, it's great to hear that, like at least you got a really good book out of it. And it's not just, something you look back on as like, oh, I'm never doing that again.
People keep asking me for the second edition and the second volume or like the next book. I'm like, well, actually, I might say yes. But there are consequences, right?
Yeah, absolutely. Yeah. Awesome. Well, I think that's a good spot to wrap things up. Tim, thanks so much for talking to me about the book, and thanks for writing it. It's an excellent book, and I'm just glad to have had the chance to talk to you about it.
Nice. Hey, thanks so much, Richard.
Thanks for listening to this episode of the GOTO podcast. Head over to gotopia.tech to discover lots more content from the brightest minds in software development.